Today, we're going to learn about multiplying two vectors using an operation called the cross product. Why is the cross product important? Well, previously we learned about scalar multiplication. Multiplying a vector by a scalar ends up stretching that vector, shortening a vector, or rotating a vector. We then learned about another type of vector multiplication in which we call the dot product. Multiplying two vectors using a dot product yields a scalar. And we saw that the dot product is useful because it allows us to determine how much of one vector lies along the axis of another vector. Now we're going to learn about the cross product. The cross product has lots of applicable uses. The cross product can allow us to determine the torque that a force exerts about a point in space. That's very useful if you're an engineer and you're designing the next electric motorcycle that will have insane amounts of torque. The cross product will help us understand and better define nonlinear motion, such as circular motion. It allows us and provides an opportunity for us to calculate the area of the plane that's described, or the area of the region of space described by two vectors. And the cross product can also be used to help us find things like volumes of parallelepipeds. This is just a small fraction of all of the uses for the cross product. So let's define the cross product. This looks rather imposing. I'm going to read it out, and then we're going to talk about it. So let A vector with an x component, a y component, and a z component, and B vector having an x component, a y component, and a z component, be any two vectors in space. Then the cross product of A vector and B vector is the vector A cross B defined by A cross B, and I'm going to write this out. A cross B. So when you are multiplying using the cross product, we use this multiplication symbol, and this multiplication symbol has a very specific meaning. When it's in between two vectors, it says that we multiply those vectors in a certain way to get a new third vector. So we call that multiplication symbol a cross because it's two lines that are crossing each other. Now, in evaluating the cross product is a vector. So it's a vector with an x component, a y component, and a z component. Now, the x component of the cross product involves the y and z components of the two vectors. The x component is the y component of vector A times the z component of the second vector B minus the z component of the first vector A times the y component of the second vector B, and that's along the x-axis. What I want you to notice right now is this term contains parts of all three coordinate axes in a rectangular coordinate system. Notice this corresponds to the x-axis. This corresponds to the y-axis. This corresponds to the z-axis. And then we have it corresponding to the z-axis, corresponding to the y-axis. So I want you to notice if we are finding the cross product along a particular axis, it involves the components of the two other axes. For example, if we look at the y component of the cross product of these two vectors, here's the y component. I know we are going to have our first vector and our second vector. This term is going to be a minus. Here's the first vector and the second vector. Well, since this is the y component, those two vectors, those two components that are inside the parentheses must correspond to the other axes in space. So in this case, it must correspond to the z component of vector A multiplied to the x component of vector z minus the x component of A multiplied to the z component of vector B, such that this term has all three coordinate axes represented. And then we're going to add that to the z component. So the z component is along the z-axis. We're multiplying the two vectors a and b, so I'm going to write ab minus ab. And for the subscripts, this is the x component of vector A times the y component of vector B minus the y component of vector A times the x component of vector B. Again, the formula, each term of the cross product must contain a representation of all of the other components of our coordinate system. Now, this is a long formula, and to be frank with you, I don't have this memorized. I know how to figure it out if I thought hard enough, because again, I know that if we're looking at an x component, the two products or the two terms within the parentheses must contain the other two axes. However, do we do the z-axis first followed by the x-axis, or the x-axis first followed by the z-axis? That can be hard to remember. So in determining the cross product between two vectors, I will mostly use another technique for evaluating the cross product.